Hi, today we'll start with a new module, the fifth module. It contains two topics. One is graph coloring and this matrix representation. So we'll start with graph coloring. Okay, graph coloring has these many topics are there. Okay, it's very interesting to know what's graph coloring. Okay, so let's suppose you have a graph G like this. Suppose you have a graph G like this. Okay, so a coloring problem basically means coloring all the vertices in such a way that no two vertices have the same color. Okay, so suppose I am giving a color, maybe I'll call a color red here. I cannot give a color red here, I can give blue, maybe I'll give some green here or yellow here. Okay, so coloring all the vertices in a graph in a such a way that no two adjacent vertices have the same color is called a coloring problem. It's very simple thing. Okay, so one way of coloring is you can give different colors to all the vertices. That will give a one way of coloring. Another way of coloring is that, so basically here also in the same graph I can also color in a different way, that is R. Okay, so suppose I am giving a red color here, I am giving a blue color here, again I will give a red color here, again I will give a blue color. Okay, so in the same graph I have colored in different format. Okay, again I can color in different way, like I can give red here, yellow here, again blue here, red here. Okay, so using four colors I have a colored, I have using two colors I have colored, I have using three colors I have colored. So basically the idea is that you should color the vertices in such a way that no two vertices should have the same coloring. So such a coloring is called a proper coloring of the graph. Okay, it's called the proper coloring of the graph, and such a graph which is being colored using proper coloring is called a properly colored graph. Okay, so what's a proper coloring of a graph? It's basically coloring the vertices in a graph in such a way that no two adjacent vertices would have the same color. Okay, so it's called a properly colored graph or a proper coloring. Okay, so in this section or in this module we are interested in a graph in which the colors used are minimum. Okay, so basically we will be interested in coloring the graph in such a way that we use the minimum number of colors. Okay, because if you are using the many number of, if you are using all the colors as many as the number of vertices, you will need, when the graph becomes big, you will be needing more and more number of colors. Okay, so that's not a good idea. So what we will do is that we will try to optimize the thing. We will try to make sure that the colors which are being used are minimum in number. Okay, so such a problem we will be considering in this section. So we will study how to find the ways or how to find the minimum number of colors which are required to properly color a graph. Okay, so I hope it is clear. So this is the idea here. So this is a graph and there is a properly colored graph is being drawn here. This is a Peterson graph. It's a very important graph. Okay, so basically in this graph we have colored the vertices in such a way that no two adjacent vertices have the same color. Please go through these two graphs. You can see that here. So this is called a proper coloring of the graph. Okay, so even in proper coloring, we can give you can actually color the vertices with maybe as many colors. Okay, so as the number of vertices, so here there are 10 vertices are there. I could use 10 colors. Okay, so I can use 10 colors. Here they have used 3 colors, so I can use 4 colors, 5 colors, whatever maybe. Okay, so the basic problem we will be interested in, basically we will be trying to find the minimum number of colors which are required to color this graph. Okay, so such the minimum number is called the chromatic number of a graph. Okay, so what's a chromatic number? Chromatic number is basically the minimum number of colors which are required to properly color a graph. Okay, it is usually denoted by the symbol kappa. Okay, or we'll call the graph as a kappa chromatic graph. Okay, so these are the main ideas here. So what's I have given two more concepts here. What's a chromatic number? Chromatic number is basically the minimum number of colors required to properly color a graph. Okay, such a graph is called a kappa chromatic graph or a K chromatic graph. Okay, so I hope it is clear what you mean by chromatic graph. Okay, so let us now discuss these concepts again. And one more thing is that to every coloring problem we can also define a partitioning problem. Okay, so what do you mean partitioning problem? It's very simple. So suppose you look at this graph here. I can actually partition the vertices in this graph into vertices with blue color, vertices with green color, vertices with red color. So for every coloring you have a partitioning problem also. For example, here the vertices with blue colors are this one, vertices with red colors are this one, and vertices with green color are this one. Okay, so associated with every coloring problem, you can also define a partition problem. Okay, and there is nothing special with vertices. You can also define coloring problems in terms of edges, so that you have to color the edges in a graph in such a way that no two edges have the same color. or you in a planar graph you can also define color in terms of the regions. Okay, so you may have seen actually coloring problems in terms of this regions only. For example, in your lower classes you may have seen some atlas or maps. Okay, even if you look at the India map, you can see that the states are colored in such a way that no two adjacent states will have the same color. Okay, so basically this coloring problem can also be extended to edges or even regions also. Okay, so we will be extending into regions later when we study 4-color problem and also 5-color problem. So I hope it's clear. This color, the same concept of coloring in such a way that no two adjacent objects have the same color can be extended to edges as well as regions also. Okay, so this is the definition of a properly coloring graph. You can see this, painting all the vertices of a graph in such a way that no two adjacent vertices are the same color is called a proper coloring of a graph. Okay, it's a very simple thing. Okay, for example, if you look at this example here in this, it's the same graph. Here we have used different number of colors. Here I have used 1 2 3 4 5 colors. Here we have used 1 2 3 4 colors have been used here, and here also only 3 colors have been used here. So basically this is called a proper coloring of a graph. So we can actually properly color a graph using any number of vertices, any number of colors. Okay, but we will be particularly interested in the minimum number of colors which are required. Okay, so a graph that requires kappa different colors for its proper coloring and no less is called a kappa chromatic graph, and the number kappa is called a chromatic number. Okay, so basically what's a chromatic number? We can define it like this. It's basically the minimum number of colors which are required to properly color a graph is called a chromatic number. Okay, so and similarly, if you look at this graph, we can say that this graph we have been colored using 3 colors here. So basically, what is the chromatic number of this graph? I don't know the chromatic number. Let us try to understand it better. Okay, so before that, I'll give you some examples here. Suppose my graph consists of only one vertex. Okay, what would be the chromatic number of that graph? It would be 1. Okay, similarly, if my graph consists of isolated vertex like this, okay, none of the vertices would be adjacent, still I can give the same color to all the vertices without affecting the adjacency, because none of the vertices are adjacent here. So basically this is also again one chromatic graph. Okay, suppose I am taking an edge like this. Suppose my graph consists of an edge like this. What is the chromatic number of this graph? Suppose I am coloring the first vertex with 1. I cannot color this vertex with 1, so I have anyway 2 colors are required. Okay, so if a graph contains an edge, definitely it will be 2 chromatic or more. For example, suppose my graph is like this. Okay, so it contains one edge is there. So definitely its chromatic number would be greater than or equal to 2. So if there is an edge, definitely the chromatic number would be greater than or equal to 2. Okay, for a single edge it is basically 2. So other graphs I don't know, we'll have to find devise other methods. Okay, and similarly let me ask you one more example. Suppose I am looking at this graph here. Suppose my graph is a cycle like this. What is the chromatic number? Can I find it out? Anyway, the chromatic number would be 2 or more. Okay, because there is an edge there. Suppose I am coloring this graph with 1, this vertex with 1. I will have to color this vertex with 2. Okay, this one also. If I am trying to minimize the colors, I'll also color this with 2 because they are not adjacent here. And similarly, I can give the color 1 here, so that we have used the minimum number of colors. So using exactly 2 colors, we have colored this properly, colored this graph. So the chromatic number of this is actually 2. Okay. In particular, if your cycle has, suppose you are a triangle like this, cannot think of the chromatic number here. So if I color this one with 1, I cannot color this vertex with 1, so it have to be different color. So again, I cannot color this with 2 because they are adjacent. I cannot color with 1, should be 3. So if it is if you can make an observation here, if there is an odd cycle there, you will require 3 colors. For example, if you are taking an odd cycle again, I will take one more odd cycle for you. Okay, so basically, okay, 5 colors are used. Suppose I am giving 1 color here, 2 color here, again 1 color, 2 color, again I cannot give 1, 3. So if it contains an odd cycle, graph, it will be 3 chromatic. If it contains an even cycle, you will require only 2 colors. Okay, so if you look at this graph here, anyway it has, so basically it is 2 more, its chromatic number would be greater or equal to 2 here, and you can see that 1, 2, 3, 4, 5. There is an odd cycle lying here, so it requires actually 3 colors. Okay, so at least 3 colors are required, but we have actually painted the entire graph using 3 colors itself, so it's basically this graph is 3 chromatic. Okay, so this is basically some observations I would like to make here. Okay, now one more observation I would like is, what can you say of complete graphs? What can you say about complete graphs? So okay, before that, one more thing we will just have to stress here that, so in coloring problems we will only be considering simple graphs. Okay, we will only be considered simple graphs because even if there are self loops like this, it will not affect the coloring. Okay, or if there are parallel edges here, we are only looking at the vertices here, so therefore the parallel edges and also the self loops will not affect the coloring, so we will only consider simple graphs. Even disconnected graphs can be reduced to the problem of simple graph by taking the components individually. Okay, so there is no need to consider disconnected graphs also, because you can consider each of the content components separately. So we will only consider simple graphs here. Okay, so only simple graphs will be considered for us. Okay, and now we'll make some remarks here. Already told you that a graph consisting of isolated vertices, only one chromatic. A graph with more than one or more edges is actually at least two chromatic. If it contains exactly one edge, it is two chromatic. More than one edge, we don't know, we'll have to find it out. That is why it said at least two chromatic. Okay, and similarly complete graph. When you're discussing complete graph, you can say that the complete graph, each vertex is adjacent to every other vertex, right? For example, if I look at this graph here, this is a complete graph K4 here. So you can say that this vertex is actually adjacent to each and every vertex. So if I give color 1 here, I cannot give color 1 anywhere else. Okay, so there should be 2 here. Now 1 and 2 are adjacent to this one, so I should give different color here. Again 1, 2, 3 are adjacent to this one, I should give 4 color. So basically if there are n vertices in a complete graph, you require n colors. So complete graph on n vertices is always n chromatic. Okay, and also taking the discussion further, suppose your graph contains a complete graph. Suppose there's a part of a, suppose your graph is like this, it contains a triangle, it's a complete graph. Suppose my graph is like this. Okay, so you can see that this graph already contains a complete graph of 3 vertices there. So this graph would be at least 3 colors are at least required here. Okay, so since this is contains a complete graph of 3 vertices, at least 3 different colors are required. It can be more or it can be correct exactly 3, but at least 3 different colors are required here. So if a graph contains a complete graph of R vertices, it will be at least R chromatic. Okay, so if it contains a triangle, it should be at least 3 chromatic. Okay, so one simple idea. Okay, and the circuit example also we have discussed. If it contains an odd circuit, you require 3 colors. If it contains an even circuit, you require only 2 colors. Okay, now we will discuss an important theorem in this context here. Every tree with 2 or more vertices is 2 chromatic. Okay, it's a very simple theorem, so also very important. So idea is very simple, you will be using geometry to discuss it, but you can see that a tree is always, you know, it's a connected graph. Okay, a tree is a connected graph without circuits. Okay, and also it contains 2 or more vertices, so therefore it will always contain an edge. Okay, so that means it will be at least 2 colors are required, so at least 2 is needed. Okay, so that's one idea. So why is it so? Because my graph contains 2 vertices, so that means since it's a connected graph, it should contain an edge, so at least 2 different colors are required. Okay, so we'll prove it now that exactly 2 is enough. Okay, so how will you do it? So basically take the tree, take any vertex in that tree. Okay, for example, my tree is, suppose my example, my tree is like this. Okay, suppose my tree is like this. Choose any vertex. Suppose I am taking this vertex as my main vertex. Suppose I call it as V. You can choose anyone you like. Okay, now give a color 1 to this V. Okay, so I'll color this vertex V with color 1. In the next step, what I'll do is that I'll color all the vertices which are adjacent with V with color 2. I'll color all the vertices which are adjacent to V with color 2. Okay, so after you do that, in the next stage, now look at these adjacent vertices. That is, look at this vertex with color 2, vertex with color 2, vertex with color 2. Now color all the adjacent vertices of those vertices with color 1. Okay, basically, so this has no adjacent vertex again, this has no adjacent vertex here, this has one here, so I'll color it with 1. Again, this is adjacent, so I'll color it with 1. Okay, so in the first stage, color the vertex V with 1. Now color all the adjacent vertices of V with color 2. In the next stage, color the adjacent vertices of those adjacent vertices with color 1, and you repeat the process. Okay, so in the next stage, I will look at the adjacent vertices of this vertex and this one. This has no adjacent vertex again, so I'll color this one with 2, 2. So in such a manner, at such a fashion, color all the vertices in the graph. Okay, so using 2 colors, color all the vertices in the graph. Okay, now we'll show that this is actually a proper coloring. I'll show that this is actually proper coloring. What is proper coloring? That is, no 2 adjacent vertices have the same color. Okay, we'll show that no 2 adjacent vertices have the same color. Okay, so I hope this coloring pattern is clear to you. Okay, for example, we have taken a tree here, we have taken a vertex here, 1 here, and we'll be coloring all the adjacent vertices with 2, and we'll be coloring their adjacent vertices with color 1, and so on forth, so that every vertex is actually colored. Okay, now you can see that all the vertices which are at odd distance from D, odd distance from V, have color 2. Okay, so for example, if you look at this vertex, this is at distance 1 from V, it has color 2. This is at distance 1 from V, this is color 2. And similarly, this is at distance 1, 2, 3 from V, it has color 2. Okay, so all the vertices at odd distance from V has color 2. And all the vertices at even distance from V have color 1. Okay, so all the vertices at even distance, if you look at this vertex, this is at a distance 1, 2, 2 from V. This vertex is at distance 1, 2, 3, 4 from V. So all the vertices at even distance from V have color 1. Okay, now so also we can know that this is a tree. So between any two vertices there is only one and only one path. Okay, so between any two vertices there is access only one and only one path in the tree. So if you have to reach one, you will have to go through this path itself. Okay, so we can see that no two adjacent vertices can have the same color. So can two adjacent vertices have the same color? If two adjacent vertices have the same color, you can see that one vertex would be at even distance from V and the other vertex would be at odd distance from V. Okay, one vertex would be at even distance from V and the other vertex would be at odd distance from V. Okay, one vertex would be at even distance from V and the other vertex would be at odd distance from V. Okay, so but you know that in a vertex which is at even distance from V has color 2, color 1, and a vertex which is at odd distance from V has color 2. So no two adjacent vertices can have the same color. Okay, so is that clear? So how will you show that no two adjacent vertices have the same color? You know that this is a tree, there is only exactly one path between two vertices. Suppose you are taking a two adjacent vertices, you know that one vertex would be at even color from V and other vertex would be at odd color from odd, and one vertex would be at even distance from V and the other vertex would be at odd distance from V. Right? Suppose you are taking these two vertices here. Okay, so this is a distance 1, 2, 3 from V and this is a distance 1, 2, 3, 4 from V. Okay, and now if it is at odd distance, it will have color 2, and if it is at even distance, it would have color 1. So that means no two adjacent vertices have a same color. That means this is a proper color. Okay, so this is the idea here. We have elaborated this proof here. Just go through it. It's a very simple thing. If you just look at the diagram and try to understand, it is very simple. Okay, so you have seen that every tree is actually two chromatic. So every tree is actually two chromatic. Okay, and moving forward, okay, a graph with at least one edge is two chromatic if and only if it has no circuits of odd length. Okay, so this is also a simple theorem. So please go through this. So this one is actually, you will see that every tree, this theorem was actually every tree is two chromatic. Okay, so now the reverse problem. So next problem we will be discussing is, are all two chromatic graphs trees? Okay, we are going to think of the reverse problem. So we have now discussed that every tree is two chromatic. The reverse problem is, are all two chromatic graphs trees? Okay, it's not generally true. So that's the so we are going to give a characterization of two chromatic graphs. So a graph with at least one edge is two chromatic if and only if it has no circuits of odd length. Okay, a graph with at least one edges is two chromatic if and only if it has no circuits of odd length. That means it can have circuits of even length. Okay, so that means every two chromatic graphs are not trees, but all trees are two chromatic. Okay, so that's a simple idea. Okay, now let us try to prove this one. Okay, now we'll prove this theorem. Okay, so the theorem is a graph with at least one edge is two chromatic if and only if it has no circuits of odd length, or you can say that if it contains only even circuits. So if it contains only even circuits. Okay, so suppose your graph contains only even circuits. We'll assume that the graph contains only even circuits, and we'll show that it is two chromatic. That is one way. Okay. The other way is we'll have to show that if a graph is two chromatic, then it has no circuit. So this is an if and only if conditions of both ways you have to prove. So in the first way I'll prove the reverse one, that is how it contains no circuits of odd length. That is, it contains only even circuits, and then I'll prove that it's two chromatic. And the reverse way, that is a graph with at least one edge is two chromatic, then it has no circuits of odd length. That also will prove it. That we'll actually prove it using the contrapositive method. Okay, that is, I'll assume that it has a circuit of odd length, then I will show that it is not two chromatic. Okay, so this is an if and only if condition. So you have to prove it in two ways. That is, first you have to show that if a graph contains at least a graph is two chromatic, then it has no circuits of odd length, and similarly if it has no circuits of odd length, you have to prove that it is two chromatic. Okay, so both ways are easy. The second way is very easy actually. If you have to prove that if a graph is two chromatic, then it has no circuits of odd length, we'll prove the contrapositive way. So what is a contrapositive? So if you know it is P implies Q, contrapositive means negation Q implies negation P. So suppose I need to prove that a graph is too chromatic if it has no circuits of odd length. It has no circuits of odd length. Okay. Okay. So if you're looking at the contrapositive, it will be it has circuits of odd length, then it is not too chromatic. Okay, then it is not too chromatic. We'll have to prove this if it is the contrapositive. Okay, because P implies Q, the contrapositive is negation Q implies negation P. Okay, now suppose it has circuits of odd length. For example, it has a triangle. What is the result? So if it is a triangle, you know that you need one color here, you need two color here. Again, this you cannot use the same colors here. So basically, it will not be too chromatic. So if it has circuits of odd length, it cannot be too chromatic. So one way is easy to prove. That is, a graph with at least one edge is too chromatic if it has no circuits of odd length. Okay, so that result we will be proving using the contrapositive method. That is, I'll assume that the graph has circuits of odd length. I'll show that it is not too chromatic. It's very simple. Because if it has circuits of odd length, you know already that it is 3 chromatic. So it is at least three colors are required. Okay, so if there is a circuit of odd length, at least 3 colors are required. Therefore, it is not too chromatic. So that one is actually easy to prove. Okay, in the second one, that is actually you have to show that. Suppose a graph has no circuits of odd length, you have to show that it is too chromatic. That we will be doing here. Okay, the other one is actually very simple. You just by using applying analytic logic, you can do that. Okay, so in this result we'll prove that suppose we contain a graph with circuits of cycles of only even length here. So, okay, suppose I am taking a graph in which contains only cycles of even length. We'll show that it is too chromatic. Okay, so I hope it is clear. So this is an if and only if condition. So you have to show that suppose the graph is too chromatic, then it has circuits of it has no circuits of odd length, and the reverse one, that is suppose it has no circuits of odd length, then it is too chromatic. Okay, that's the second one we will be doing here. Okay, suppose the graph has no circuits of odd length. That means all the circuits of the graph are even only. Okay, or the cycles or all circuits of the graph are even only. Okay, then we will prove that it is too chromatic. Okay, how will you prove it? Okay, so what you do is that you take a spanning tree of G. Just take a spanning tree of G. Okay, so you know that since the spanning tree of G is actually a tree itself, it is too chromatic. The spanning tree would be too chromatic. Okay, now what I'll do is that in the spanning tree, I'll be adding back all the other edges. In this spanning tree, I'll be adding back the other edges of G. Okay, or in other words, I'll be adding the codes to the spanning tree to obtain the full graph. Okay, so what I'll do is that first of all I'll take the spanning tree of G. Okay, and I know that it's too chromatic, so I'll color all the vertices of the spanning tree in with 2 colors. Okay, now what I'll do is that I'll give back the edges of the graph back to the spanning tree. I'll give back the edges of the graph back to the spanning tree. Okay, and I'll show that this actually, if you distribute back the edges, still the proper coloring is not disturbed. Okay, so look at this one here. Okay, so for example, suppose this is your spanning tree. Okay, my graph was a different. Suppose my graph was this one. Okay, so suppose this is my spanning tree here. So I will be giving back the codes of this graph back to the spanning tree. So that I would to obtain G, I'll have to add codes to the spanning tree. Okay, so how will the codes be coming? Suppose some codes will be coming like this. Okay, maybe one code is like this. Okay, or maybe another code is like this. So this may be, so when I complete the codes, maybe I'll be getting back the original G. Okay, so what I will do, first I took a graph G, I took its spanning tree. First I took a graph G, I took its spanning tree. Okay, I colored the spanning tree. Now I am giving back the codes to the spanning tree. Okay, to obtain the original graph. I am giving back the codes to the spanning tree to obtain back the original graph. Okay, so this is the idea here. Okay, so the codes when I draw, it will be coming like this. Okay, so let us analyze this a little bit closely. Suppose can a code be like this? Can a code come to the spanning tree like this? Okay, so if a code comes to the spanning tree like this, you can see that the proper coloring of T is disturbed. Okay, the proper coloring of T will be disturbed if a code comes like this. But can a code come like that? Okay, so if a code comes like that, you can see that the 2 vertices would have the same color. So this color of T will not be valid for G. Okay, so if a code comes like this such that its endpoints have the same colors, the coloring of G would be disturbed, and this coloring of T cannot be extended to coloring of G. Okay, that's the idea. Okay, so first you took a spanning tree, you colored T. Okay, I am trying to look whether this color could be extended to G, but in G there are codes. Okay, so there are other edges than those in T. So when I add those edges, suppose one edge has two vertex of same color, then you cannot extend the coloring of T to G. Okay, is that correct? Okay, now can such codes happen? So if such a code happen, what will be the problem? So if such codes exist in which it has the same endpoints with it has the endpoints with the same color, what will happen? You will be getting here odd cycles. So if you look here, you will be getting a triangle here, or some other example. If you look at some other example here, okay, suppose I am adding here another edge. Okay, I am adding an edge between two vertices of the same color here. Is that possible? Here also there will be no edge like that, because this graph does not contain odd cycles. Or I'll add an edge like this one between these two. Still that edge cannot be possible because this graph does not contain odd cycle. And similarly, this edge cannot happen because again this graph cannot have odd cycle. So basically all the codes will not be between cannot be between two vertices of the same color, because if it happens, that means there will be odd cycles in the graph. Okay, so the codes will be with colors of different vertices, like the vertices of different colors. For example, the code would be like this. Okay, so if it is like this, there is no problem in the cycle, because you can see that the cycle is of even length. Or it may be like this. It can be like this also. Okay, so if it is like this also, again 1 2 3 4, again the cycle is not disturbed. Okay, basically, so that means in this graph, since there are no odd cycles, the codes will only be between vertices of different colors. Okay, so if it happens, what will happen? That means in that case, the coloring of T can actually be extended to the coloring of G. Okay, the coloring of T can actually be extended to coloring of G, and since T is colored using two colors, this graph is two chromatic. Okay, it's a bit abstract, but if you look at the example, you will easily understand it. Okay, so what is the idea? So first you took the graph G, then you took the spanning tree, you color the spanning tree with two colors. Now you are going to add back the vertices of the edges of graph to the T itself. You are going to give back the codes. Okay, so when you give back the codes, what will happen? So can you extend the coloring of T to G? Okay, you can extend the coloring of T to G only if there are no two adjacent vertices with same color. Okay, suppose when you add the edges, what will happen? Suppose I am adding an edge here. Okay, that means this vertex and this vertex have become adjacent and that has the same color. That means you cannot extend the coloring of T to G. Okay, if this happens. Okay, but can that happen? It cannot happen, because if it happens, what will happen is that there will be even cycles present there. There will be even cycles there. Okay, so there cannot be codes between vertices of the same color there. Okay, if there are codes between vertices of the same color, that means there will be odd cycles there. Okay, but it is given that this graph does not contain odd cycles. Okay, so it will not happen. So that means here the codes are between vertices of different colors only. Okay, so and if it is like that, it will not disturb the coloring pattern of T in G. Therefore, G can also be colored using just two colors. So that is the idea. Okay, so just go through this again and try to visualize this proof using the diagram. Only if you understand the diagram, you will try understand this graph. Okay, that is the idea. Okay, so if it has no cycles of odd length, it will be two chromatic, and the reverse one also we have discussed also, that is suppose it has cycles of odd length, it will not be two chromatic. That is the contrapositive method. That is, suppose it has circuits of odd length, you will load at least three colors. So we have actually used the contrapositive method here. Okay, so this is also a interesting theorem. Okay, now to the final section, we will discuss a upper bound for the chromatic number. Okay, so these three theorems are very important because there is no much theorem to be coming from these sections. So please study these proofs, try to understand them. So one upper bound for the chromatic number. Okay, so what is it? For any graph G, the chromatic number will always be like less or equal to delta G plus 1, where delta G is the maximum degree of a vertex in G. Okay, so for any graph G, the chromatic number will always be less or equal to delta G plus 1, where delta G is the maximum degree of a vertex in G. Okay, it's very easy, simple proof. We'll prove you will prove this using induction. Okay, we'll prove this using induction. Okay, suppose your graph has just one vertex. Okay, just one vertex. That means your delta G is actually 0, because the maximum degree is actually only one vertex is there. Okay, then what is the chromatic number? You will anyway require one color, therefore in that case you can see that chromatic number is 1, which is less or equal to this delta G plus 1. Okay, that is one idea. Okay, now assume that the result is true for a graph with n vertices. Suppose you have a graph with n vertices, then assume that it is true that the chromatic number is less or equal to delta G plus 1. Now we'll prove that the theorem is true for a graph with n plus 1 vertices. We'll prove that the theorem is true for a graph with n plus 1 vertices. Okay, suppose we are taking a graph G with n plus 1 vertices. Okay, we'll have to prove this one. Okay, now what I'll do is that I'll just delete one vertex from G. I'll delete one vertex from G. Deletion of the vertex means I'll delete the vertex and all the edges also which are incident on this vertex B. Okay, so I'll just delete this vertex. So I'll call G1 as maybe some G minus a vertex B. Okay, now this G1 will have how many vertices? N vertices. Therefore for G1 you can say know that the chromatic number of G1 would be less than or equal to delta of G1 plus 1 by assumption, by induction assumption. Okay, now the maximum degree of this delta G1 will anyway be less than or equal to the maximum degree of G, because G contains more edges. Okay, so delta of G1 plus 1 will always be less than or equal to delta G plus 1, because G1 is obtained from G by deleting a vertex V and also its edges which are adjacent on V. Therefore, the maximum degree of G1 will always be less than or equal to delta G plus 1. Okay, so that means your G1 can actually be properly colored by using delta G plus 1 colors. You can actually, so even that much is not required, you just require delta G1 plus 1 colors is required. But to prove this theorem, I'm taking it in this format. Okay, so this G1 could actually be properly colored using just delta G plus 1 colors. Okay, now what I'll do is that I'll now give back, now I'll just color G1 using all these delta G plus 1 colors. Okay, now what I'll do is that I'll attach back the vertex V to G1. Okay, now I'll put the vertex V and all the associated edges back to this G1 to obtain G. Okay, now we'll have to color this V also. Okay, so all other vertices have been colored, you will have to color this V also. Okay, now you know that the V has what can be the number of adjacent vertices of V? What can be the maximum number of adjacent vertices of V? The maximum number can be the maximum degree possibility. It need not be the maximum degree, but the maximum number can be the maximum degree. So at maximum it can have delta G adjacent vertices. Okay, so at maximum we can have delta G adjacent vertices. Now there are delta G plus 1 colors are there for you. So even if all the other vertices have been colored with delta G, still one color will be left for you. So yeah, that leftover color could be used to color this V. Okay, so even if you add back the vertex V, you won't require new colors. The existing delta G plus 1 colors is enough for you. Okay, so that means using delta G plus 1 colors itself, you could color your entire graph G. That means the chromatic number will always be less than, it can be made to be delta G plus 1 or it will be less than that. So the chromatic number, the minimum color will always be less than or equal to delta G plus 1. Okay, so very simple proof, very simple idea using induction. Therefore this is true. Okay, so what is it? First you prove for n is equal to 1. Just in one vertex you need one color. You assume it for n is equal to, just you assume it for a graph with n vertices. Okay, then you take a graph with n plus 1 vertices. Okay, so from that graph you will have to prove this result. So what I'll do is that I'll just delete a vertex. So I'll be getting a graph with just n vertices. The result is true for that graph. Okay, after that what will you do? The result is true for that graph then. So we'll carry over, so using the result this will carry over this result in for that graph. So that means that graph would be colored with delta G1 plus 1 colors, or in particular it can be colored with delta G plus 1 colors, because this delta G1 is less than or equal to delta of G. So this G1 could be colored with delta G1 plus 1 colors. Okay, now you color all the vertices like that. Now you give back the vertex V. Okay, so when you give back the vertex V, you will be getting the original graph. So now you have to color the original graph. Okay, now delta G plus 1 colors are available for you to color. But already you know that the maximum number of adjacent vertices for V is actually only delta G. So using delta G plus 1 colors, when you color everything, still one color will be left for you. Okay, so that leftover color could be used to color V without taking extra color. Just one color is with one leftover color is there, that is just sufficient to color this V. So that means this delta G plus 1 colors could be used to color this graph G. Okay, so this is true for n plus 1 also, hence by induction that is also true. Okay, so this result is also very important, so they can ask you this one also. So please try to study that also. Okay, so that's all. Okay, so thank you.